spheres having radii 2r and 2r such that both the spheres have equal surface charge density. Now, uh, we have to find the charge on each sphere at a point of time. So let us now look at this problem by first explaining what the surface charge density means. So surface charge density comes with the standard formula, which is sigma equal to E multiplied by epsilon, or like how we say it, it's equal to E is equal to sigma. So sigma, you write it as 6. So 6 inverted is called sigma. Sigma is equal to E epsilon 0. Now you are also familiar with the formula of E. E is equal to KQ over R squared, remember, because the electric field is always measured for a point charge, right, at a distance P from a unit charge. So that's why electric field has only one charge present. So that's how eventually we most of you would have probably seen it here. This step, your teacher would have written the step directly probably on the board. So that's where kq epsilon 0 by r squared is written, and then we write the standard value of k as well. K is equal to 1 by 4 pi epsilon 0, and hence when k is equal to 1 by 4 pi epsilon 0 is written, that's where you eventually get the final equation which your teacher has written on the whiteboard, which is q by 4 pi r squared. Now, interestingly enough, the area of a sphere is given by the formula 4 pi r squared. So that's where the formula for surface charge density then becomes simplified as sigma is equal to q by area of sphere. Okay, because the formula in the denominator matches the formula for area of a sphere. So this equation is valid only in the case of a sphere only, just to reiterate that point here. And now we are in a position to write solve for our question, because our question asks us to find out the situation when the surface charge densities are equal. So whether it is r and 2r, their surface charge density are, so sigma 1 equal to sigma 2, which means now I can substitute the values. Q, remember this is the same value of charge, right, capital Q. So I'm just going to rewrite it as capital Q. Capital Q over, now here's the difference here, 4 pi r squared is equal to Q over 4 pi 2r the whole square. So now this very clear, right? It's a very clear differentiation happening here, q1 and q2 here. So at the end, when we are eventually solving it, we are going to get a relation between q and q. So 4 pi gets cancelled, and the r squared also gets cancelled. Eventually I'm just left with q2 is equal to 4q. So q2 is equal to 4q1 is the answer that I am left with. So that's a charge, that's a relationship between each of them, right? So since I now know the relationship between each of them, now it's very much straightforward, right? How the charges are now distributed. So since now we know for a fact that both of them, and now the relationship is like q2 is equal to 4q1, now I can like finally solve the answer, because the total charge, okay, so the total charge q net, which is equal to q2 plus q1. Now I can just simplify this relationship, because I want to find out what is the charge present on them. Because I have the relationship between q2 and q1, I can now substitute it. So that will give me the relationship with the total charge as well. So the total charge eventually comes down to, say, the numerator I will have 5. So so the total charge is 5, which means at any point of time, right, one sphere, if whatever be the value of the, whatever be the value, 5 is the number. I have to split 5 equally among both of them. So the value 5q1, or whether it's 5q1 or whether it's I'm representing in terms of fraction, right, whether it's represented in terms of fraction or q1, the answer will still remain the same. Let me just simplify. My computer is, yes, so my computer was hanging for a moment, so I just had to come back now. Now remember our relation. So Q, either I can write it in two forms. I'll just solve both of them just to make sure it's clear. 4q1 plus q1 equal to q net, or the second way of doing it is by using the fraction method. So if it's fraction, then it's going to be q2 plus, that's right, q2 by 4, because q1, if q2 is equal to 4q1, then q1 is equal to q2 by 4. So that's a fractional method of getting the answer as well. That's where the final answer for q net will become 5q2 by 4, or I will have the option also having the answer 5q1. Both answers are correct, because remember, I'm representing the total charge in terms of either q1 or q2. Now this question can have two variations, like you can have different set of options here. You can have fractional options here, depending on the options given in the questionnaire, or you can have like a, you know what, you can have a you can have, yeah, so 5q1 is equal to q net. So if I know now the total charge percent is 5q1, which means at any point of time, right? Yeah. So q2 is always equal to 4q1. Let's just keep this in mind, which means the charge at q2 after distribution, right? Yeah, so that means q1 will have only q1 charge. So this should be the set of options that you need to take, because the total charge is still 5, remember, adding up to 5. Okay, so the same equation must now apply even if it is fractional as well. So if I find 5q2 is equal to q net, right? So the total charge 5q2 is equal to q net. Again, apply the same relation. No need to boil your head over it. 5q2 is equal to q2 is equal to 4q1, right? This is like constant. We found that even in the very beginning, right? So if q2 is equal to 4q1, what is q1 then? Very easy, right? Just subtract the values. 5q2 by 4 minus 4q1. Right. So minus q1 by 4 will give me the answer that I seek, which is equal to q2. And this will simplify and give me the answer. q2 is equal to q2, which means again it is correct. So this gives me the answer that I'm looking for, which means that now I have successfully solved. So I can choose any of the relevant relationships, the relevant options that are available to me at any point of time as well. So that's how you solve for the final equation. That's how you solve for the charges distributed on each individual spheres. Thank you.